Good evening, everybody. So my name is Yelena. I'm one of the teaching assistants in data analytics program. Tonight we're going to cover the decision tree classification using R, and this session is being recorded. All right. So here is our agenda, and we're gonna do a little bit. I'm gonna go over the data pre-processing that we need to do for the data sets that I'm working at. We are working with, and then I'm gonna explain what the training and test set is, and I'm going to show you two implementations of the method, C and R part, all right? And we're gonna discuss the required packages and how to run the method. We're gonna work on the result interpretation, and we're gonna show you how to evaluate the module on the test data, and there is a bonus tonight. It's a fancy plot, so once we get to it, I'll show you what I'm talking about. And then we're gonna have some question and answers. So let's get back to business. I'm gonna go ahead and share my screen. Share my screen. There we go. So here is an R Studio. What I did, guys, I wrote a couple scripts that we're gonna go over today. So let me minimize this window, right? So we're going to look at two scripts, but the data set that we're gonna use, this is academic data set, and we are going to predict if our student is at risk of academic failure. So dependent variable is gonna be, it's gonna track if the student is at risk or if the student is not at risk. And other variables include the GPA, and then if the student, how many courses the student needs, and more, right? How many clubs does a student belong to, etc. So to start with, what we need to do is we need to set our working directory, right? And the working directory is a directory where R is going to look for my file by default, right? So I have a folder on my external hard drive that I call data sets. So now what I do, I'm going to run this command, and it sets the working directory. Okay, when I do that, it sets the working directory to the folder called data sets, right? Now I have a file called riskstudents.csv that I'm going to read right now into R data frame, and I call my R data frame RS, right, which stands for risk students. And here a header equals true. It means that the first row in my data is header, so I want to read the headings, right, the variable name from my data, and separator is a comma because the file is comma delimited. So let me go ahead and run this, right? So here it is. I have 6,203 observations and 22 variables. And what I forgot to do is I forgot to add the summary command, right? We have to run the summary command and rs, right? Summary. Now, what I wanted to show you here is that one of the columns, one of the variables here is it has the same value. Look at this state, right? Our state variable has the same value for all instances in the data set, right? So more likely this variable is not interested for the purposes of this classification method. This variable is going to be not interested because all instances in the data set have the same value, right? So we want to remove it. One more thing that you want to pay attention to in general is that you want to check if the data set has a unique identifier, right? Those variables need to be removed because unique identifier does not really tell us much whether or not the student is at risk in this case. Now, another thing I wanted to point out here, that first of all, I'm going to remove the state, but I also want to remove the county because we've got 62 levels, all right? So you had an option. One option would be to group some of the values, but I'm just going to remove it, all right? Now here are my data preprocessing steps are right here. So basically, in order to remove the variable, one way to do that is just set it to null, uppercase null, right? So let me do this, and I'm gonna run this. Now, this is what I did, and then you can run the summary command again to verify that the variable was in fact removed. Or alternatively, you can run the names command, and the names command is going to list you the variables that you have in the data set, and you can verify that these two variables were removed, right? And now remember, removing the variables only removes it from the copy of the data frame in memory. It does not remove the variable from the data set on your hard drive, right? Now, what I want to do here is, first of all, I have to install the package. Right now, I'm running the C3 implementation of the method. And to run this implementation of the method, I have to install the package. If you may remember, RStudio comes with some built-in packages, right? But Party is not one of the packages. So what you'll do is, I don't need to run this because I already have this package installed. But in your laptop, you'll need to run this command, install packages. The first input parameter is Party, right? And here, dependencies equals true. It's because some functions in a Party package depend on the functions in other packages, right? So if another package does not exist, right, it's going to install it for you. Now, I have a package installed, but the problem is, at the moment, my environment does not know what that package is. Even though the package is installed, it's not available. So to make it available, I have to load it into memory. To do that, you may either run the library command or you may run require command, right? And here is the package name, require party, right? Here it is now. You see this in red? It's not an error message. In this case, the message in red, it's telling me that the package was loaded in memory. Now, we already did the data preprocessing. Other possible data preprocessing that you may need to do is handling missing values. And you will see what's happening when a variable is used as a splitting variable. It's unclear what R is going to do with missing values, right? Now what we'll have to do is we have to split our data into the training set and test set. But before we do this, this is very important. We want to make sure that our results are reproducible, because some work may or may not be done in one single sitting, and also because I might make a mistake. I might delete a variable unintentionally. I should be able to recreate the results, and I should be able to recreate the same results, right? So you are going to run setSeed command. The number that I put in here does not matter, all right? I just like to use 1, 2, 3, 4. And let me run this. Now here, what I'm doing is I have to split my data into the training set and test set. We use the training set to build the model, right? So basically, my data consists of the set of student profiles. And I want to identify the student profiles of the students who are at risk of academic failure. I'm using my past data, right? I'm using the data to build the model so that when I have a new student, I can look at the values of my variables and I'm going to see where, into which profile, so to speak, my student fits in better, right? And I want to be able to build a model that I can use to predict if my new student is at risk of academic failure. But the problem is we don't want to overfeed the model to the training data, right? So that's a reason we have to split the data into training set and a test set. After I build my model on a training set, I'm going to evaluate how well or how bad my model performs on a test set. So here, I'm creating two data frames, training data and a test data. So let me go ahead and run this, 3 commands, right? Now, so that remember that we have to build a model, we use the training data, and we validate the model on a test data. And we have to do that because we don't want to overfeed the tree to the training data, right? Now, we are going to build the model. The function name is the C3. Now it has two required input parameters. There are optional input parameters, but we'll get to it. The first input parameter is called a formula. This is a formula. It specifies which variable is dependent and which variables are independent. Now, dependent variable is also called a target variable in some books. It's a variable that we want to predict, right? In our case, the variable is risk. We want to know if a student is at risk or not, right? Now, tilde, right, follows the dependent variable, and then after tilde, we need to list the variables that we're using as predictors. But the wildcard dot means that I want to use all variables but risk, everything but risk, as my predictors. Here, it means that the data, I'm using the training data, right? So these two are input parameters. Let me go ahead and run this. And I'm going to store my model in a variable called model, run. Okay? Now, what I need to do is I want to see, let's see the textual representation of the model. I'm going to run it here. There we go. So now if I scroll up, here is my output. And what it's telling me here, the first part, it's telling me which method I ran. C3 stands for conditional inference tree. 25 terminal nodes, it means that the tree has 25 leaf nodes. And I think it will make sense once we plot the tree. So what I really like to do is I like to show it in parallel. I like to plot the model, and we can look at the textual and visual representation at the same time. So here it is. It's a little bit crowded. So let me do zoom. Now, what it's showing here is that my first splitting variable is the number of times that the student missed the class, right? Absences. And the first split, I'm asking myself a question. Did the student miss the class 2 or less times? If yes, I'm going to take this branch, this path, right, to the infirmary visit. If the student missed the course more than twice, I'm going to take the right branch, right? That's what it's doing in here. And this is just the node number, right? So let me take a look. See this? This is basically a similar representation, but it's a textual. Let me scroll down, and scroll up rather. See this? It says absences, right? Less than 2. And actually, it's showing me, well, now see this is my first split, right? It's a number of absences. So now what I'm going to do is, if number of absences is less than 2, then I'm going to drop down to this node right here, infirmary visit, right? So I'm here right now. Now, what I'm going to do is, I'm checking if the student looked for medical help less than 0, it means never. Then I'll need to check the student GPA, right? This is what it's saying. And if the student GPA is below 2.6, then this is the leaf node that we ending up at. For each leaf node, we look at how many instances fall in that node, and then we look at how many instances are at risk and how many instances are not. And the class of this node is gonna be dominant value. The dominant value is gonna be a class, right? Well, I realize that it's a little bit crowded, right? A little bit hard to see, but what we could also do is we can make a, let me show you. The plot has another option. There is a simple plot and there is an extended plot. I was showing you, we were looking at the extended plot. So to look at the simple plot, right? Let me zoom in. So the simple plot, basically, instead of showing the distribution for each node, what I see here is that I see the number of instances that fall into that node. Like for instance over here, I have 62 instances that fall into that node, and here is a percentage of instances that are at risk and that are not at risk, right? And it's taken the dominant, right? So the highest value would be not at risk, right? Then it's a class. That's basically how we do it, right? This is how we interpret the model. We have to start from the top, and then we are asking ourselves a question. If number of absences is greater than 2, we are looking at the club membership, right? And if the club membership is less than 0, in other words, if the student didn't join any clubs, then we look in here, right? And we keep on going until we reach the terminal node, right? So let's minimize it, but basically this is your textual representation. It's a little bit harder to read, so that's why I like to look at it in parallel. I like to have the copy of the tree and the textual representation in front of me. Right? Here it is, also here. Now, if you notice that the nodes here are numbered, and I also have the same number in here. So I can look here and look at the textual representation at the same time. And notice that this star here, it means that this node is a terminal node, right? And 18 means that 18 instances, 18 variables fall into this node, right? So now what we'll do here is that I need to show you something else. When I just did the model, when I just ran the model command, I output the entire model, right? But what if I'm only interested in a specific section? For instance, what if I want to see everything starting from node 5, this piece, right? What I need to do is, there is a function called nodes, right? And as an input, it takes my model, and here, this is a starting node. So basically what it means that I'm going to display this branch right here, right? If I find number 5, see here, this is number 5, I'm going to show this section right here that emanates from number 5. This is what I'm doing. Look at this. If you look at this, right, 5 is connected to 6, right? And then 6 has the 6 has a criteria, right? It leads to 8. Well, basically what I'm trying to say here is that we can display only portion of the tree, right? So see this, node 6 is another splitting criteria. Its looking class hours is the number of hours that student has completed toward the graduation, right? So that's what it's doing. It's just a portion of the tree. So you have a model and a starting place where you want to start. So we look at the plot, right? By default, the plot type is extended. Type is an input parameter for the plot. And so you have the simple and extended. Extended is a default, right? And a simple is, you have to specify simple. It's not going to show the distribution. It's only going to show the percentages, like this, right? Now what we can do is, there is more. Look at this, how these terminal nodes are not at the same level, right? What we could do, there is another input parameter called drop terminal. When the drop terminal is true, look at what it's going to be like. See this? The leaf nodes is going to be just at the same level. Basically, here you just control how the tree looks like. That's what it is. Right? So now, let me go and close it for right now. Now what we need to do is, we need to find how accurate our model is. And I'm going to show you a little trick here. Now, this is how you build the confusion matrix, right? Predict function, predict model. This here will predict if the student is at risk or not. It's going to use the training data, right? It's going to use the training data. And we want to do the cross tabulation. We compare the value that the model returns, right? Predicted value with the actual risk value. Remember, trained data $, right? And risk is one of the one of the variables in the data frame, right? So here, risk here, this is going to be the actual risk value. So we want to compare, but take a look at it. Sometimes we are looking at it and it's very difficult to tell where is my actual values and where is my predicted. So let me show you a trick here. The table command has another argument called DNN. And what I'm going to do here, I'm passing a list. Look at this. The first one right here, predict, model is a predicted, and the second one is actual. See this? So I'm going to add labels to the matrix. And that way it's going to be much easier to read. So here I would know that these labels, right, the column labels over here, row labels are going to be predicted values, and the column labels are going to be actual. So that's basically the same confusion matrix that you saw before, but I just showed you how to add this label. It's going to make your homework very much easier to follow. Just it helps you, right? So now, what we also can look at it this way. Here it is at risk, right? We have 361 students who we predicted that they're at risk of academic failure, and in fact they're actually at risk. So this is called true positive, right? We predicted they are at risk, and they are at risk. Now here we have true negative, because we predicted that student is not at risk, and the student in fact is not at risk, right? We also have false positives, where we predicted the student might be at risk, but the student is not. Or we also could predict that the student is not at risk, but the student is at risk, right? We can use this matrix to determine the classification accuracy. Look at it this way. There is a pattern. These numbers on the diagonal, right? This means these numbers, right? They're accurate predictions because the predicted value matches the actual value. So, to calculate the classification accuracy, we have to take the sum of these two numbers on the diagonal and divide them by the number of instances in the training set. Right now, we are doing evaluation on the training set. Another way to do it is this. I wrote this for you here. So basically, if over here we're going to count the values where predicted is equal to the actual. And here we are dividing by the total. See this? Length is going to take the number of instances in the training data. Do you remember? Length, right, is one way to get the number of instances in the data set. And here basically here we are saying this is conditional, right? Condition. If predicted value equals if predicted value equals the actual value, right, then it's gonna count. And let me run it, and this is gonna give us 0.89. So the classification accuracy is about 89%. Now we are going to evaluate our model on the test data. And what we want to see is, we want to see if the classification accuracy for the test data approximately the same as the classification accuracy for the training data, right? Because if the difference is too big, it means that the model there could be a chance of overfitting and underfitting, right? So we want to make sure that the numbers are close. So what we'll do now, this time I'm going to store the predicted values in a variable called test prediction, right? Here, this is my function predict, and I'm going to pass my model variable. Here, I'm going to say that new data equals test data. Remember, we divided our data into training and test, so now I'm taking a test. And the method is going to be class. By default, it's class. But when we do another implementation, it's slightly different. You have to explicitly specify class. But now what I'll do is I'm going to run this, right? And this will store the predicted class into this variable. That's one way to do it, but I want to make sure you see different ways, right? So if I wanted to see what's actually in there, we're going to run the head command, right? When we run the head command, remember that? It will show us the first 6 values. Right, so this is your best friend, because sometimes you want to see what actually happens. See, you have this not at risk, this is predicted. Now what I want to do, I want to build my confusion matrix, right? And I'm using this input parameter. And after this, you're going to have a copy of the script. You'll have a copy of this file. So now let me run this. So here is my confusion matrix for my test data, and what I want to do is let me calculate the classification accuracy here. See this? It's very close, which is good, right? It means that this is good, because if suppose for a training set, if my classification accuracy is 95%, but if for the test set it's just 70, that could indicate the overfitting, right? It would indicate something wrong. For instance, I was trying to fit my model to work really well only for the training data. But then what happens when I get a new data? See, we have problem. Now, here, I want to show you some additional input parameters for the tree. We can control how deep the tree is. So if you notice here, right, if I zoom in, see the depths we went 1, 2, 3, 4, 5, right? There are up to 5 splits. We can control the depth. So that's basically sort of like pruning, right? So let's see. This is what I'm doing. I'm building another model. I call it A. And here, this is my formula. This is a dependent variable, tilde, followed by dot. That means I want to take all variables besides my dependent variable. This is a data frame. And here, a control. Control is an input parameter. And here, this is a C3 control, max depth. And I'll show you where, when we get to it, I'll show you where to read the documentation on C3 control. So C3 control allows specifying I can control how deep I can go, right? The number of splits. I can control the stopping criteria. Like, for example, if my node has less than 100 instances, I want to stop splitting, right? So there is this. So here, let me run this. So we created model A, and now I'm going to preview my model A. See this? And let me plot this to show you what I'm talking about. Now, here it is. So, something to keep in mind that the depth of the tree affects the classification accuracy, right? So if the depth is too big, there is a chance of overfitting also, right? So now here it is. See this? We have the first split on absences, right? Then if number of absences is less than 2, they go in here, check if the person needed the medical help. And here is the leaf node. See that this is an extended representation of the decision tree, of this tree. And here it's showing you the percentage of students who fall into that node who are at risk and who are not at risk. Here there are 25 students in this node. We have 147 students right here in this node, right? So this is dark color means not at risk apparently. So if you missed 2 or less courses, and if you didn't look for medical help, and if your GPA is above 2.616, more likely you are not at risk for academic failure. That's what it basically means, right? So if I have a new instance, a new person who missed the class 3 times, right? Missed the class 3 times. What should I do? I should follow this branch right here, right? Next step, I'm going to check if the person is a club member. Suppose that the person is a club member. I go here, then I'm going to check the student GPA. And if the GPA is less than 200, if the GPA is below 200.8, right, then we fall into this node, right? So this is basically how we read this. So this is a not at risk is a dark color code, right? So if we end up being here, then it means that we are 60%, there is a 60% chance of a student is not at risk, because out of 209 people, 60% were not at risk. That's what it means. And then when I look at this node right here, out of 507 students, 65% were not at risk of academic failure. So this is basically how we do. When you have a new instance, you just start from the top and you traverse the tree. Then you look at which terminal node you stop at, and then you look at the dominant class at the terminal node. This is how you do, right? So now when you have less splits, right, the classification accuracy may drop, right? Right, but however, we need to keep in mind that if you do too many splits, you may overfit the model to the training data. So now let me go ahead and close this out. Here, this one is, it tells you when to stop splitting, basically. So this is another control parameter. So let me do this, and let me do this, and do this. Now, if I look at this here, zoom in, it's basically telling me the minimum number of nodes when it should stop splitting, right? It's basically, I can control, I can say, if I have less than 200 nodes at the time when I split, if I have less than 200 instances at the time when I split, right? If I have more than 200 instances that I have to split, right? If I have like 150 I should not be splitting anymore. And minimum bucket, it means that each leaf node must have at least 300 instances, right? So each terminal node needs to apply at least to 300 students. So this is just basically the conditions that I can pass, right? Those are just basically the optional parameters, and I'm gonna plot model C. So I was basically showing you what you could do. So now if I zoom in, see this? I don't have any nodes with that have less than 300 because I said the minimum bucket equals to 300. It means my leaf nodes need to have at least 300 people, right? Now look at this. Does it really make sense? I don't think so. It does not really make sense because take a look at this class hours. Regardless what class hours is, I'm still not at risk. See this? It does not really make sense. So I have to keep on splitting. Right? That's the whole idea, see? And if you look here, well, it does not really make sense much. And another reason is that my data set, the class is a little bit out of balance. Because if you look at the original, over here, if you look at the original data, you can see, well, I guess you would have to look at the summary. You would have to look at the summary to see the summary RS risk, right? So let me show you something. Oops. Do you see this? It's not balanced. I have 991 at risk and 5,212 not at risk. But I think the model did pretty well because we have approximately the same classification accuracy, right? And 89, it's very good. Now what I can do here, I'm showing you where to get the help. To read more about the C3, you put a question mark in the C3, right? So that will open the help page on the C3. And here you have different options. See this? I showed you how to use control, and you read the rest of the options at your leisure. Here you can read more about the C3 control, how you can control the splitting criteria, basically. And we did the minimum split, it's the minimum sum of weight. So it's, in other words, if you don't have the specified number of observation at the splitting point, then the split should not occur. And here it's showing me the minimum number of instances that should fall into each terminal node, right? So basically just different input parameters that you can play around with. Now here, example C3, basically what it's doing, it's running the C3 method on ARCT. This is one of the built-in data sets that comes with R. And if you need to see an example, sometimes if you put example in the method name, you'll see it. Like I can click through it, and it will build the model for me. It's just showing you an example on one of the built-in data sets. That's what basically it is. So some packages, they come in, some R packages come in with an example, right? So that's basically what I'm showing. And notice in this example, the variable, the dependent variable might be the numeric. That's why you don't see the, that's why you see different visualization here, right? Now, this one is here is also useful, the VNet party. So let me run this. And this is supposed to open the PDF file with the documentation about the package. That's called VNet. Some packages have it, some packages don't. But this is a very good resource to learn more about the package. Now what I'm going to do is I'm going to show you a different confusion matrix implementation. The package name called caret, right? So you need to install this package and dependencies equals true, because it's highly possible that this package could depend on something else that we don't have installed, right? And here, well, I put it as a bonus because this is not explicitly discussed in your homework walkthrough, but this is something that could add value to your assignment, because you'll see what it shows now. So here, let me run this require, because look, I have a package installed, right? If you scroll down, you'll see it. I have it installed. But the problem is the package is not available because I never loaded it into memory. So let me do this quickly now. Now it's loading the package in memory. And now what I'll do is I'm going to build confusion matrix. And what I did, guys, for you, I'll show you what I did. So now here it is the confusion matrix. And here I'm passing this input parameter because I want to label where I have the predicted values and where I have the actual values. I want to put my labels to make this more readable, right? But what I did for you guys in the slides, and you will have a copy of the slides. Oops, you will have a copy of the slides, and I will reopen the file, or actually, let me stop sharing for a second. We have a file. We have a file in here. So let me go back. I put this together for you. I took this. This is the information, additional information that the output gives you. And from this output, you can calculate the accuracy rate. So basically, the classification accuracy, see this? It's already giving you that it's 89%. Initially, when I displayed the confusion matrix for you, I physically ran the command to calculate it, but here it calculated it for me already, right? Then I can do, this is called the sensitivity. I want to determine the proportion of the true positives, right? True positive means that the student is at risk and it's actual at risk, right? And I want to determine the percentage of the, see, I'm taking the true positive divided by total actual positive, so that's a sensitivity. And so on. I can calculate these measures, right? I can calculate these measures. That's what basically it's given me. And if you want to add value to your assignment, you can in fact do a little bit research and describe how this helps your analysis. That's a good place where this is a good way to add values to your assignment, right? Not the exercise, but for the assignment, this could add value. Now let me go back and share. But basically here I'm just trying to show you this is a different way to do the same task. So let me go back to share my screen again. All right. So here it is. Right? So I was basically showing you that this exists. Now, I'm going to show you a different implementation of the decision tree. And you may like it better, maybe, or you may like the C tree better, but I want to make sure that you have an option. Now, it's called R part, recursive partitioning. And basically the difference is that it's using a different criteria for splitting. Here, I'm not going to run this again, but I did put it here just in case, because after this lecture, right, I'm going to give you a copy of the script and a copy of the file. So in case you want to be able to follow along, right, I put all commands in here. So here we are setting the working directory. I don't need to run it again because I already ran it today, right? I already ran it and I did not exit my R. Now here I have to install the package rpart. I commented out this line because I don't need to install it twice, but you will need to install it, and you set dependencies equal true, because this package depends on existence of some other packages, right? Now, the package is installed, but the package is not available because I have not loaded it into memory. So to do that, I need to run require command or library command, right? Alternatively, I could find my package over here and just check the checkbox next to it, right? I can do it. But if I do it this way, I want to add the command. If I do it this way, R is going to run the command on my behalf, but I want this command to be in my script because I want to be able to easily I want to be able to easily reproduce my work, right? All work that we do must be reproducible, right? So here, R ran this command for me. It's using library, right? Now what we do here, we got to the data pre-processing, and I already ran it, so I'm not going to repeat this, right? I remove the state, and I remove the county. And then here, I set seed just in case. Let me rerun these commands. Let me rerun it just in case. So we are setting the seed. It's a random number. And I also want to split my data into the training and test data. Now we're going to use the training data to build the model. Now I'm going to call rpart function. Rpart stands for recursive partitioning. Here, the first input parameter is my formula. The first part of the formula is a variable that I want to predict, followed by tilde. And here, wildcard dot means that I want to use all my other variables as predictors, right? And this is nice that this method follows the wildcard character. You don't need to type all variables, but some methods don't. You'll see it in a couple of weeks from now. But this method follows. Now look at this. This is my training data, and the method is class because here I want to predict the class, right? Now let's go ahead and run this. And now I want to print my actual model. See, here it is. It looks differently, right? It looks much differently. But here, let me show you what it's doing. Here is a root node, right? Here, it shows me the number of students at risk and not at risk. So here, this is not at risk, more likely. And this is at risk. It's showing me how many students at risk and not at risk I have at the root node. And remember that this is the training data, right? So we have to be looking at the right here. This is the training data, right? So the total, this is the total number of objects, right? Oh, rather, see this? This is the total number of observation. I goofed. This is the total number of observation that fall into this node, and 695 is the number of the not at risk. That's what it is. Okay, so this is the total number of instances, and this is the number of not at risk. And here are basically the percentages, right? The other way around, sorry. No, we are good, yes. So now here we are splitting again. I'm sorry, I'm bad. This is at risk, okay? 695 students are at risk because we have not at risk. We have more students not at risk than students at risk. So my bad, okay? So here it's showing you the percentages. I realize it's a little bit confusing, so what you could do is you can just look at your data and you can see how many instances you have at each level, right? So this is total, and here are the percentages. Now I'm going down, I'm looking at it. Look, my splitting variable is absences, right? So I'm asking myself a question. Is the number of absences greater than 3? Yes, it is. Then this is the number of students, right? And I keep on going. I keep on going. This is how I evaluate this. Then I'm looking at the club membership and so on. So for each node, basically, I'm given how many students I have at risk and how many students I have total. See, this is actually loss, right? So this is how I need to be looking at it. I was looking at it a little bit here. So now, here the star also indicates the terminal node, and the dominant class, the class that falls into the lymph node is going to be the dominant, right? The dominant value, if the student is at risk or not, that's going to be the class. So basically, we follow the same steps, right? Now we're going to, this is something else I wanted to show you. Which variables are important? The variables that are important are the ones that are used to split the tree. If you notice that not all variables from the dataset are used to build the model. Look at it, how many variables we have. We have about 20 variables, but not all 20 variables are used as a splitting variable, right? So this is what it's going to do. Variable importance is basically going to show you which variables are important, and the higher the number, the higher it is importance. But something to keep in mind, if the variable is used for the first split, it does not necessarily mean that the variable is going to be the most important. You have to look at how many times. You have to look at if it's used just once in a tree or if it's used somewhere else, right? You just need to look at, there is no right or wrong answer, but when you're answering that question, you want to check at which variables are used in the tree, which variables are not, right? Like, see, this overall GPA is used, and you may notice that some variables are used more than once, right? Like we are comparing the GPA in different branches of the tree, right? So it must be important one way or the other. So here it's listing the important variables for me. Now let's plot the tree. There is more than one approach to plot the tree, and I'm going to show you. This is the first command you run. Next command is just going to plot the skeleton. This is just the tree skeleton, right? There are no labels on it. And now we're going to add the labels. Use n equals true because I want to see the node numbers. Now let me zoom in. Here is my tree. I realize that it does not look that pretty, but I'm going to show you the more beautiful representation of the tree, definitely. But, well, it's readable. We can still read how many students are fall in each node and how many students are at risk and how many students are not at risk, right? So, for instance, this leaf node, right, the dominant value is not at risk, which is 305, and 108, it means it's at risk, right? So we start from the top and we traverse the same way. Now I'm going to show you this is more beautiful visualization, but you have to install the rpart.plot package. This is another package called rpart.plot. And we run this command, right? Now, what I'm going to do is, this is going to look much better. First, we're going to print, this is just this one. I'm going to show you several options. This is the first version, first variant, right? I'm not showing the node numbers, and I'm only showing the dominant class and each node, right? But I'm not showing the percentages. I'm not showing much details. I'm not labeling I'm not numbering my nodes, and I'm not showing the percentages, how many students are at risk, how many students are not at risk in each node. But the problem is, sometimes I want to look at this in parallel, right? Sometimes I want to look at these numbers here and at the tree, right? I want to have it side by side and analyze it when I'm doing my result interpretation. So what you could do is, this is an option, n equals true. This will add the node numbers to the tree. Oops. This is because I highlighted L. When I run the command, I need to put my cursor on top. I should not be highlighting part of the command. Okay, so now I added the node numbers. It's much easier for me to have this tree here and look at it here at the same time, right? Because I know which node I'm looking at. But I still don't see everything I need. This is called extra. Extra equals 106. I just got it from reading the documentation. This is gonna show you the percentages, and you would need to either maximize this window or zoom in to see more details, right? But I'm sure if you, at your leisure, if you play around with the properties or with the text can be adjusted, the text size, and so on. I'm going to leave it up to you, but I'm trying just to give you an idea here. See, this basically what it's doing is that it's showing you that the dominant class at this node is at risk, and it's showing you the percentage of people who fell into that node who are actually at risk. Now I'm going to show you how to do the confusion matrix. Remember, we have a training set and a test set, right? So first we're gonna do on the training set, we're gonna check the classification accuracy. And first I use the table command. But do you remember, this is kind of hard to read. I don't know which dimension is predicted, which dimension is actual, so I'm going to use an n parameter. I like to label it, right? So here I have the true positive, the true negative, right? So now I can use this matrix to calculate the classification accuracy. So in this case, it's about almost the same, right? It's close to what the other model predicted, remember? Now what we can do is we can evaluate the model, this model, on the test set, right? And I called it model 2. So now here I'm going to store my predicted values in a variable. I'm going to call it prediction. So here this is my model, and this is the test data, right? This is the new data input parameter. And here, it means that I want to predict a class, right? Because see this, if you look at the function predict, you can check which input parameters it takes, and you can check the options, right? In this case, you have to say class. You need to say class for the tree. And now, let me run this command here. And now I'm going to build the confusion matrix here, right? And now what I also can do is I can use the other implementation in the carrot package that I showed you, right? So let me do this. Let me run it. I did not load the package into memory right now because I already loaded and I did not restart the R session. So now let's take a look at this. You see this? You want to check the classification accuracy, which is 0.89. It's approximately the same as the test data. You don't want to see if it's couple percent or a few percentage difference, no problem, but we don't want to see the 90% accuracy on the training data and 50% on the test data that indicate that the model might be overfitting to the training data, right? Now here we also have this option to control the tree depth, right? And I wanted to show you how to do this. There is a control parameter, right? This is how you do this, and this is just shows you how the model looks like. So you can adjust the depth, and you can adjust the splitting criteria, right? That's another splitting criteria that you can adjust, and I'm just showing you. And this adjustment affects the classification accuracy. Yes, it does. So that's something to keep in mind. It affects the classification accuracy. And I'm just going to leave it for you to leisure to experiment. When you get a copy of this script, feel free to check the confusion matrix for this model, right, model 5, and you'll see what I'm talking about. But right now, I'm just running it. So now, some of you might be wondering what's an optimal size of the tree, and I'll show you. I'm going to show you how to do this. There is a CP table. This model has a property. This is not available for C3 representation, but this is available for the R part representation. The CP table, so let me look at it. There is more than one way to look at it, but basically it's looking at the number of splits in the tree, and you want to look at this relative error. And if you plot it, you want to look at the inflection point, right? And the point where it is an inflection point is probably the ideal depth of the tree, and I'll show you. Here it is, this command, you want to plot this. This is basically showing you the ideal depth of the tree. In this case, it's 5. See that it's showing you how the error rate changes. This is the relative value error, and how it changes with the depth of the tree. The more levels the tree has, the lower the error. But we need to keep in mind that we may overfit the tree, right? So this is just the complexity chart, and wherever you see the inflection point, that's probably the optimal depth of the tree, right? And here is another way to print this table right here. Print CP. It's an alternative. Now, to read more about the recursive partitioning method, you type the question mark and you type R part, right? So this will take you to this page, and here you can read more, right? You can read about different parameters that the method takes, and you can explore and play around. Here, it's just showing me, do you remember one of my input parameters is recursive partitioning control, where I can control the depth of my tree, right? For instance, I want to stop splitting after the 3 levels. So basically here, I want to read about all options that I have, and it's in here. Now here, this package, it does not have a vignette, but it has an example. If I put example, and if I put the name of the method, right, I can see an example, and it's going to use one of the built-in data sets to do an example for me, and I can just run through it, right? So this is just an example on built-in data set, and yeah, that's a dependent variable, and this is independent. I think it's a column data set, looks like it. Yes. Now let's so here it is, and now this is my bonus. And this is for people who have been either attending this WebEx or watching the recording or both, and people who have been paying undivided attention. For this, you would need to install library is Color Brewer and then Rattle. These 2 libraries, and this is called Fancy Plots. And secretly, if in your in Leo, in this week course content, the tree that you see, the picture of the tree on iris data, was made in R. It was done in the Rattle tool, and that's a class that was used. Now, see this? I can run this to load the package. I have to run either required or library. When you do it, you would have to install the package first. You would have to install the package first. And now I'm going to load this package. Now, see this? It's showing me the notes in red. This is not an error. This is just the feedback. Now, the method name is fancyplot, and I'm going to do model 3. I created that model somewhere up here. I'll just pick model 3. Okay. And this is how it looks like. Isn't it nice? I'm gonna zoom. It just looks more... It's using a different color code for each class. That's what it's basically doing. Green stands for at risk, and blue is not at risk. And if it's a light blue, it means that the node has a mix, so to speak, right? The color code changes from blue to green, and based on the value of the dependent variable. And I can also change my color, right? This is how I do it. And you have to use the available colors. Oh, see this? It's doing them side by side. It's because somewhere in the settings. Oh, I see why it's doing it. It's because when I was running the examples set this property to plot 2 plots per page. And if I don't like it, this is a command I can run, def off. This will reset my plot. So now when I plot this, it's going to show 1 plot per page. It should show like this. Yes. It's because when I ran the examples, somewhere code in an example reset to show 2 per page. Now I'm showing it 1 per page. And see this? We start reading it from here, right? And then we say, has the person been absent more than 3 times? Right? And we keep on going, we keep on traversing this tree, right? And then we end up at the terminal node, and the terminal node is going to be the class of an instance. So then when I get a brand new instance, I'm going to start from the top, and I'm just going to traverse my tree, just by asking myself a question, right? I'm going to be asking, is the number of absences greater than 3? And I'm going to be looking at the GPA, and I'm going to be looking at the club membership if needed, and I'm going to be looking at the infirmary visits. And here is basically how to change the color. Now here, I put this web page where you can look at more examples of this beautiful plot, but this is something for you to explore at your leisure. And this is a package that was used to create the tree in the course contents. All of this was done in R. So I talked for about over an hour. Now it's time to check what questions we have. And some of you have been working. Yes, what is this? Can you explain the drop terminal? Oh, the drop terminal, that's an excellent question. So basically, the drop terminal, this is just how I want my picture to look like. So here, if I plot this, if I do the drop terminal equals true, this is how it looks like. It means all my leaf level or terminal level nodes are going to look lined up like this. The nodes are going to be lined up. See this? They're on the same line. It does not matter where the terminal nodes occur. They're going to be brought all the way at the bottom. But, on the other hand, if I set it to false, which is default, if I set it to false, see this? It's not aligned. This is just basically cosmetics. It just controls how I want my picture to look like, right? So in this case, I did not line them up. It's just the difference in a picture, right? See this versus this. It's the same model, but I'm just changing how it looks like. I hope I answered the question. Because, well, sometimes if you're doing a paper, Oh yeah, sure, you're the most welcome. Yeah, sometimes if you're doing a paper, well, you don't want to be spending too much time on this, but this is something that you may want to look at your leisure, and it will help you learn more R just by reading documentation. And yes, what I did for you, I'm gonna stop sharing for a second. Oh, oh, you're the most welcome. You're the most welcome. Yes. So let me stop sharing for a second, and what I did for you, I put together on the slides. I'm just giving you some examples. Here is just example of the appearance. Right. I just wanted to show you how these parameters can change how this looks like. All right. This is just the appearance. And here I just put this, I labeled a little bit for you, the first split, this is a leaf node, and so on. And I'm using different shapes just to show the splitting criteria. Yeah, so basically what I did, let me go back. For you here, I outlined which packages you would need to have for each function, right? And oh, the asterisk, excellent question. I just got a question. What are the asterisk means? Asterisk for the RPath model is also terminal node. It's a leaf node. Yes. So here is a list of packages, right, that we use today, and it also depends what else you're trying to do. It depending on what data pre-processing you do, you may or may need more. Yes, and I was expecting somebody to ask this question. Nobody did, but I did not discretize. I didn't do the discretization because the method kind of did it internally for me. If you look at the tree, how it split the GPA for me, here is, oh, that's probably too small, but if you look at the tree, you will see. How should missing values be handled for decision tree? I would recommend you to handle them. And you can, if the variable is numeric, you can just replace it with the mean. You can replace the missing value with the mean. Because the problem is if you have a missing values and if that variable is selected for the splitting variable, it's really unclear, at least to me, what method is gonna do. How is it gonna? We don't want to. Yeah. So we want to handle them. We want to handle missing values. Yes. But also you want to look if your variable is missing values for more than half of the instances, then probably you may decide not to use you may decide not to use that variable, right? And also it depends on a decision tree method implementation. Some methods you can say an ARM equals true to ignore missing values. You would need to also look at the method implementation that you use. But I hope I answered the question. Should we control the outliers? Well, for this one, no. For this one, no. Not for this method. That's an excellent question, Teresa. I did not do anything with outliers for this specific method. But what you're supposed to be concerned in here, well, what I did was, do you remember one of my variables? It was skewed, right? So you want to look at this. It depends. See, if the variable is skewed, if your classification variable has, suppose that I have vast majority of students in Maryland and maybe one student in other class but not Maryland, then the distribution is skewed. I may want to group the student not in Maryland into other category. So, for instance, I'm going to have the values in Maryland and outside of Maryland, something like that. That's one option. Another option is not to use a variable. So there is no right or wrong, but you'll need to explain in your assignment. You need to explain and you need to focus on the representation, right? I mean, interpretation. So, because, yeah. Yeah, let me see. Did I answer the question? because I want to make sure that your questions are answered, and I like questions. Some of you may have met me. Skewed variables, yes, skewed variables are concerned, that's right. Exactly. And also, see, there's another issue is that I'm dividing my data into training and test set, right? So suppose that I have only one student in Maryland, right? And I divide my data into training and test set. What's going to happen? We have a problem, right? What happens? I'm going to have a student with in Maryland in a training set, but I'm not going to have a student in Maryland in test set? Huh? This is kind of weird, isn't it? It's not what we want. So, yeah, this is something to pay attention to, right? So I put this together for you, just basically as a summary, and you will have a copy of this page. So here, I put the input parameters, yeah, and I put the little commands that you can run to get some help, right? And I also put same thing for the R part. That way you have a choice which method you want to use for the assignment, right? Exercise is C3, but for assignment, you want to have the choice. And here, this is something for you to, this is just more. If you want to add value to your paper, you can look into that. So let's see if we have more questions. What if you end up with a low accuracy, like 60%? Well, then you would need to look into your data set, check if you have the skewed variables. You would need to, or sometimes if it's possible that the model is not suitable for the data. That's possible too. But if the prediction accuracy, classification accuracy is low, you would just need to explain it in your paper. And sometimes you can improve the accuracy just by removing certain variables. You have to look at which variables are skewed. Sometimes you can remove, or sometimes you can group values, right? Like an example I said, suppose that we have most of the students in Maryland. Students not in Maryland could be grouped as out of Maryland state. There is no right or wrong, but what becomes a problem is that if my classification accuracy on the training set is 90% and the test set is 60%, this is a problem. It's an inconsistency, right? It means I might be doing something wrong, right? I might be overfitting. Yeah, so let me see. I like questions. Yeah, let's see. Do we have more questions? I hope I answered it. Tony, let me know if I answered the question, because I want to make sure that the questions are answered, right? So let's see what questions we have. I like questions, and I call this, yeah. Oh, sure, you're the most welcome, Teresa. Yep. What's this? Okay. Oh, okay. Sure, yes, but basically, well, basically, go ahead and oh, I see. I see what you mean. Yes. So basically, what you do is we have to look at in order to, sometimes, very often, the model does not work well for the data, and then we explain it. For some data, the neural network could do a better job, and neural network is going to be the topic for the next module, and John is going to be doing the class on this, the R class on the neural network. But that's one reason you want to try different models. But the thing is, the main purpose is not to get 100% accuracy. The main purpose is to analyze and to interpret the result that you got. If the accuracy is low, then you explain that it's low, and that's what it is. But also, Tanya, I would need to see which data set you're looking at, because there is no prescription, so to speak, right? We need to look at the data we're looking at, right? Oh, CMC. Oh, yeah. I'll have to look at this. And we have to look at which variable is a dependent variable. The CMC dataset, I think it's a birth control method, right? Birth control method choice dataset, yes. So, yes. So we'll have to look at which variables could be removed. Sometimes it could be a combination of variables. Sometimes it's a combination of things. And another thing that will help you is that if you go to the dataset description page, you may find the related studies for the data and see what methods are used in the related studies. That could be really helpful, right? You want to check, in the classroom you have a dataset description. You click on that link, and usually at the bottom of the dataset description link you can see the different, you can see, what do you go? You can see the different case studies, and when you look at the case study, it will show you what methods are used in the studies. Let me see if I can share my screen and show you what I mean. Dataset. Let me go quickly to the dataset repository. Because this is really gonna help you. So let me see one second. So basically what you need to do is you need to go to the link. One second, I'm trying to find the example. Okay. You see, I ate my okay. Let me go ahead and share my screen quickly, and I'll show you what I'm talking about. Share my screen. Here it is. Like, see this? Here is a datasets repository. It's just an example. So, for instance, if I'm looking at the adult dataset, right? Adult dataset. I click on the description, then I scroll down, and see this? I can see related papers on this dataset, and the related papers could give you a clue on which method works well for this dataset. See this? Like, for instance, the specific dataset, related studies use naive Bayes. So that could be really helpful. All right? I hope I answered the question, because here there is no right or wrong. There is no right or wrong. Oh, excellent. Yeah. So let me stop sharing. Let's see who else has questions. I like questions. So, and I call this customer service because my goal is to help you, right? So go ahead and ask questions. I'm still here. And if you don't have questions, I have questions. Remember which tree representation we went through today? You remember? We went through sys3 and we went through R part, right? And does everybody remember that we need to divide the data into training and test set? Right? You will remember that? So 70 and 30, but that's what I use, but it's not necessarily, you may see the different splitting percentages in a book. That's something else to try. Any other questions about the decision trees and anything like that? Well, going once, going twice. If you don't have any more questions, then everybody, hope you have a good night, and I want to thank everybody for joining today. And the recording will be available in a classroom, and I'm also going to post the script, the dataset, and the PowerPoint presentation. Thank you. I'm going to stop the recording.